This video is for the second day of Section 5.9 regarding volume. Yesterday we did volume by revolution using the disk method. And just to recap that, we started out with using vertical slices because we've been calculating area first with vertical rectangles. And when we revolve one rectangle around an axis of revolution, it creates a disk or a flattened cylinder. And so when we calculate volume by revolution, we would, the volume of that cylinder, that disk, would be pi r squared times the width. And in this case, the width is going to be our dx. Pi r squared, the r of x is our y equals equation. That's going to be the radius of each disk. And then our limits of integration are the x values. And then the other part is if I asked you to revolve the area around an axis of revolution that is not the x-axis, you have to subtract the lesser function from the greater function to find the new radius of each disk. So that volume equals pi of the integrand from a to b of r of x minus r of x squared, and then times dx. So it's always the greater function minus the lesser function and then squared. And this is for disk method when you're revolving around an axis that's not the x-axis. The other part to the disk method is if we are using horizontal slices, and this is what you're going to use when we are revolving around a vertical axis of revolution. So if I asked you to revolve an area around the y-axis, this is the setup that you would use. It's no different than vertical slicing. It's a lot like finding the area using horizontal slicing. A couple things that are different are now our limits of integration are going to be represented by y values. And then instead of r of x, we have r of y. And so this is going to be an x equals equation because this is always going to give us the distance from the y-axis. So this is pi r squared and then times the width of the disk, which would be dy. So an example using horizontal slicing, it says to calculate the exact volume of the solid of the region in quadrant 1 that's bounded by the parabola y equals 4 minus x squared that is rotated about the y-axis. So now we're going to be taking the area, this is just in quadrant 1, so this right half of this parabola, and we're going to revolve it around the y-axis. So our slices are going to be perpendicular to the axis of revolution, and so this is why we're going to use a horizontal slice. Now I gave you the equation as a y equals, but in order to use horizontal slices, it has to be in terms of y, meaning an x equals equation. So rearrange this, and you'll get y minus 4 equals negative x squared. Divide both sides by a negative 1 and then take the square root, and you get the square root of negative y plus 4. So this is now going to be the radius of each disk. So when I set it up, my limits of integration now, since the area of the region is going from a y value of 0 to a y value of 4, those are my limits of integration. Then I'm going to have my radius be represented by the square root of negative y plus 4. Have to square the radius. If I were asking you to do this by hand, you can cancel out the square root and the square. Otherwise, you can just type this into your calculator. It did say to calculate the exact volume. So then you would get 8 when you do the integral in your calculator, and then don't forget to multiply by pi. So the volume of the solid that is created when you revolve this area around the y-axis is 8 pi. So I'd like you to pause the video right now and keep this up there, and I'd like you to try these two practice problems on your own or with a partner, and then unpause the video and come back to see the work and the answers to the two problems. Okay, for number 1, it says calculate the exact volume of the solid obtained by revolving about the line y equals 4, the region in quadrant 1 bounded by y equals 0.5x cubed and the y-axis. So we're in quadrant 1, and we're going to revolve the region that is bounded by the cubic and the line y equals 4, and the line y and the y-axis, sorry. But we're revolving around the line y equals 4. And so this is a case where it's still disk method, but we are not revolving around the x-axis. So that means our radius is not just going to be the equation. And so if I were to draw the vertical slice of my rectangle, we want to calculate what is this distance here. And so the full distance from the x-axis up to my line that I'm revolving around is 4. And my smaller radius is represented by this rectangle underneath the red one. And so that's going to represent r of x. Sorry. And so the radius of the red region is going to be the larger radius minus the smaller radius. And so in this case, my larger radius is just a value of 4. My smaller radius is the distance from the x-axis to that cubic, so 0.5x cubed. So then my radius is going to be 4 minus 0.5x cubed. And then the setup for the volume is the pi r squared, so my radius squared. And then since I'm going from x values of 0 to where the two intersect at an x value of 2, those are going to be my limits of integration. Calculate the exact value, you would get 80 over 7, and then don't forget to multiply it by pi at the end. The second example said to calculate the exact volume of the solid obtained by revolving about the y-axis, the region bounded by x equals y squared plus 1, x equals 0, y equals negative 1, and y equals 1. So when I graph all of these, I have a sleeping parabola. It says you are revolving the area that's surrounded by the y-axis, which is x equals 0, y equals negative 1, and y equals 1. So I've highlighted in yellow the region that I'm going to be revolving. My rectangle is going to be a horizontal slice since we are revolving around a vertical axis of revolution. And then calculating the radius is going to be the distance from the y-axis to the end of that sleeping parabola. And so it's already in x equals form in terms of y. And so my volume equation is going to be pi and then times the integral of, from negative 1 to 1 are your limits of integration since those are the y values that surround the region. And then my radius is the sleeping parabola and then squared. And then my exact answer would be 56 pi over 15. Another method that we have of revolving an area around an axis is the washer method. And the difference between disk method and washer method is that you have a gap in between the area that you are revolving around and the axis of revolution. So if this rectangle is going to be revolved around this x-axis, but I have this gap here, if I were to rotate this, it's going to be like a compact disc, a CD with a hole in the middle, or in other words, a washer, and that's why it's called the washer method. The formula for this one is volume equals, we still have pi, our limits of integration are still going to be from a to b, which could be where the two functions, if there are two, intersect. And then now we have the larger radius squared minus the smaller radius squared. And so this is really just the greater function squared minus the smaller function. Now one thing I want to point out is the difference between this and our disk method when we were revolving around an axis that wasn't the x-axis. And so the difference, that very last example before we did horizontal slicing, is that we did the larger function minus the smaller function and then we squared it. Whereas with washer method, because we have that gap, we're going to square each one of the radiuses first and then find the difference. So just make sure you know the difference between washer method and disk method when we're revolving around an axis that's not the x-axis. So our first example, it says calculate the exact volume of the solid formed by revolving the region bounded by the graphs of y equals the square root of x and y equals x squared about the x-axis. So we're revolving it around the x-axis, so then we're going to have a vertical slice. So here's our rectangle. So since we have a gap between some of the places where our rectangles would be, this is going to be washer method. Our greater radius is the function that is on top, so the square root of x, and then our smaller radius is going to be the lower function. In this case, it's x squared. And so when I set this up, my larger radius squared minus my smaller radius squared. And since these intersect at 0 and at 1, my limits of integration are from 0 to 1. And my exact answer is going to be 3 pi over 10. And then this is an image of what that object would look like if you were to rotate it around the x-axis. It looks like a bowl. The second example I have says to calculate the exact volume of the solid formed by revolving the region bounded by the graphs y equals x squared plus 1, y equals 0, x equals 0, and x equals 1 about the y-axis. And so we have our parabola here, and then y equals 0 and x equals 0 pretty much is just telling you that we're in quadrant 1, and then the other boundary that we have is x equals 1. And so the shape here is we have a rectangle and then we have this little dip here. Okay, and so we're revolving it around the y-axis, and so since it is a vertical axis of revolution, we're going to use horizontal slices. And now here's one thing, is that if you take a look at the region, I could draw a horizontal slice here, which I don't have a gap between my area and the axis of revolution, so I could use disk method here. But then when I go up past an y value of 1, now I have a gap between the area and the axis of revolution. So we're actually going to break this up into two parts. We're going to use disk method from 0 to 1, and then we're going to use the washer method from 1 to 2, and then we're going to add the two parts together. But then because we are using horizontal slices, my function that I was given was y equals x squared plus 1. We need to get this in terms of y, or as an x equals equation. So just subtract 1 from both sides and then take the square root. So the very first area that we have is its radius is just going to be 1. So from 0 to 1, my radius is 1. It's not a function. It's just that vertical line, that vertical boundary. And so the integral from 0 to 1 of 1 dy, and then times pi. Then we're going to add that to this smaller region from 1 to 2. Remember, your limits of integration are y values. So from 1 to 2, we're now going to use our larger radius is from 0 to 1 in terms of x values. And then my smaller radius is the distance from the y-axis to this parabola. And so the square root of y minus 1 is our smaller radius, and then square that. When we add these together, we get pi is the area, is the volume of the disk method that we use down here. Pi over 2 is the volume that we get for the upper part, and when we add them together, we get 3 pi over 2. The picture of what this object looks like is kind of a cylinder with a little dip at the top, like a bowl at the top of a cylinder. And then the washer method. What if we shift the axis of revolution and it's not just going to be the y-axis? So this first example I have for when we shift the axis of revolution is called the wetting band. If you calculate the volume of the wetting band that is created by rotating the region between the graphs of f of x equals x squared plus 2 and g of x equals 4 minus x squared about the line x equals negative 3. So we're using washer method because we are revolving around an x equals negative 3. Sorry, that should say y equals negative 3. Because it's a horizontal axis of revolution, we're going to be using vertical slices. So the first thing that I want you to ask yourself is, which function is greater? Which one's going to be our larger radius? And so if I were to just plug in a value, if I plugged in 0, I would get 4 for g of x and I would get 2 for f of x. So it appears that g of x is the greater function. Then, what are the limits of integration? Well, the limits of integration would be where these two functions intersect. So when I set them equal to one another, I get 4 minus x squared equals x squared plus 2. Get everything over to one side. Please don't make the mistake of, if you see an x squared on one side of the equation and an x squared on the other, that they're going to cancel out to 0. Since this one's a negative, we're going to add it to the other side, so we would get 2x squared minus 2. I factored the 2 out to get 2 times x squared minus 1, and then that's a difference of squares, so that factors to x plus 1 and x minus 1. And so our x values, our limits of integration, is going to be x equals -1 and 1. And then just remember that we're revolving it around the line y equals -3, not x equals -3. So the picture of this graph, we have an upside down parabola and our U-shaped parabola, and it's just this little tan area that we're revolving. And so I'm asking you, is the radius of the greater function still 4 minus x squared if we're revolving it around the line y equals -3? So this is our axis of revolution. And so before, our larger radius would be 4 minus x squared, and our smaller radius would be x squared plus 2. But now our axis of revolution is 3 units down from the x-axis. And so our new larger radius is not just going to be 4 minus x squared, but now we have to incorporate the additional 3 units. Our smaller radius is not just x squared plus 2, but it's x squared plus 2 plus the additional 3 units that we're moving for our axis of revolution. And so no, 4 minus x squared isn't the greater radius anymore. So now we have to add the 3 units to get 7 minus x squared. And then our r of x, our small r of x, is going to be x squared plus 2 plus 3, that distance from the axis of revolution, and we get x squared plus 5. So here are the 2 pictures that we get. Here is one of the washers, and then if you were to add up all the washers together, it makes what we call a wedding band. And so then our setup of the volume problem is going to be from -1 to 1. Those were the limits of integration we found 2 slides ago. Pi, our constant, is still out front, but now our larger radius is 7 minus x squared and then squared minus the smaller radius and then squared again. And when you calculate that, you'd get 32 pi, or approximately 100.531. This last example I want you to try on your own. And then we will go over this on the block day when we're doing our last section of volume. It says to calculate the volume of the solid by rotating the region between the graph of f of x equals 9 minus x squared and the line y equals 12 for values between 0 and 3, and these are x values. So first I'd like you to try and revolve it around the line y equals 12, and then revolve it around the line y equals 15. Try this on your own, and we will do the answers on the block day. When you get done with this example, you can get the volume 1 and volume 2 worksheets to work on for the rest of the period.